Okay, welcome to lesson 25. I'm actually going to split this into two different videos probably because we're going to talk about how hydrogens that are next to a C-O bond tend to be rather acidic, or more acidic than other CH bonds rather. And before I go into this listing right here, I want to show you, if you could recall, why any of this happens. This is known as the Ketotomer. And no, I can never say that correctly, so pardon me if I'm pronouncing it wrong again. But what that means is that to get between these two, we've got a hydrogen that's removed from down here and placed up here, which we've seen the mechanism for before, but I'm going to show it to you again in just a second. Therefore, what that means is that this hydrogen can actually come off and be displaced over here, right? So if that's the case, being in the middle or sandwiched in between two of those means that this hydrogen is relatively acidic. Now, as we move on to the next one, if you recall, these electrons are being pulled down this way. Why? Because there's an electronegative atom down here. Well, therefore, it's not as acidic here because electrons are being dislocated down here and therefore won't go into this direction quite as easily. And that's something that we see as a general trend as we move on. So, for example, this guy, this hydrogen, is more acidic than the one right here because, again, electrons are being pulled this way. And this guy, being an amide, that actually forms its own resonance structures, correct? I am going to correct. Nope, that's fine. So that's a general rule. The general rule also is that the keto form is more stable than the enol form, with some exceptions, because you know that there's always exceptions. You've seen this exist as phenol. Well, technically speaking, there is a double bond next door. But if this guy were to go through and form the keto form, then obviously the entire benzene ring loses its aromaticity, and that is not stable. So that's something that you just assume is going to stay into the enol form. The enol form is most stable here. And not all of the enol forms are as unstable as others because, like, for example, when you have a diketone here, if you have one of them in the enol form, it can actually hydrogen bond to the other oxygen, and that makes sort of a very stable intermediate. We're going to come back to this in a couple of lessons, so I just wanted to make sure that you knew that that actually existed, okay? Okay. Now, how do we actually get between the ketol and enol conversion? Well, there's two different forms. We can do both acid catalyzed and base catalyzed versions of these. So if we start with the keto form and the acid catalyzed, the electrons come and grab the hydrogen, and so we've got oxygen having a positive charge up here. So that means that this oxygen would more easily abstract that hydrogen, and electrons go up. Sorry, I missed one there. And electrons go up, and bam, there's your enol form. In the base catalyzed version, the base directly comes and removes that hydrogen from right there. That's actually going to make a carbanion on this alpha position. Those electrons move in, that goes up, and as this resonates between these two forms, this resonance structure, will grab a hydrogen, and there you go with your enol. Okay, I'm going to stop this video now and come back for the rest of lesson 25.